All right, can you all hear me okay?
Yeah.
All right. This will be a fairly short meeting. So I am in the process of grading your multimeter labs. So yours is the last group, okay? Hopefully I can get it done by this week, and I've done about a third of them. So one of the issues with the multimeter lab is this. I mean, most people did fine. I guess that one issue is this. So it really involves students measuring the current through the bulb. And so what students did is they set up their circuit like this, and then they took the multimeter and hooked it up in parallel, and this is a big no-no. Because now you've put the multimeter in parallel. So what happens when you do this? And I saw it in the video, but people didn't notice what was wrong with what they were doing. The multimeter on the 10 amp scale has a very low resistance. So what happens when you set this up? What happens to the bulb when you set this up? What do you think?
If you do it on parallel?
Yeah, if you put the multimeter in parallel, what happens to the bulb?
Wouldn't it turn on?
It would turn off. If you set it up like this, so before you connect it, the bulb is on. When you connect it like this, the bulb is off. Why? Well, think about the fact that electrons go this way. When they reach this junction, they're going to want to take the path in which the current is, they're going to be more likely to take the path in which the resistance is minimized. And so the ammeter on a 10 amp scale is going to have a very low resistance, lower than that of the bulb. And so most of the electrons are going to go this way. Very few will go this way. And so the bulb will go out. And that should tell you did something wrong. Okay? So, and then you'll get a big current. I had one student get 7 amps. The wires will get warm if you have 7 amps. Luckily, the battery's only 1.5 volts, because if you did this with your wall socket, you'd blow the breaker in your house. Okay. So if you hook it up in parallel, you're not measuring what's going through here. You're actually changing the circuit. And so that's why I said in the multimeter video, make sure that the ammeter is in series. This is how you do it. One end of the power supply to the one end of the bulb, the other end of the bulb to the multimeter, and the other socket of the multimeter goes to the other side of the battery. That's how you do it. And so the amount of current going through the light bulb will be the same as the amount of current going through the meter. And the meter is going to have a low resistance too. And so you're going to get an accurate accounting of how much current is going through here. Okay, this is completely wrong. And so not a lot, but people did that. And what bothered me was that I told the class to play around with the simulation beforehand. And if you did this in the simulation and you ran it, this thing would catch on fire in the simulation. You'd see flames in the simulation. But it was obvious to me that people didn't set this up in the simulation, because they would have known they did something wrong. Okay? So I give the class resources on the modules to help them to accomplish their assignments, and people are not using them. And so this is the result of that. Okay? So just be careful. Just remember, when you're measuring current, the ammeter has to be in series with the rest of the, it has to be in series with the component that you're you're analyzing, okay? And anyway, we're gonna have a few more labs where you're actually measuring current, so you're gonna get more practice on it. You're gonna have to get good at it because if you plan on taking Engineering 17, you have to be good at it because you're gonna be wiring some very complicated circuits in Engineering 17, or 17L, sorry. Oh, Matt, I didn't see the one you put in Discord. I should check that one out too, because I could probably add that too. Can you, yeah, go ahead and link it again. Thank you. So since your lab, you have a labs due soon, well, it's not very soon, but you have a lab due on the 29th and you have a lab due on the 5th. So right now what's due is the Ohm's Law lab. I talked about it a couple of weeks ago. And the reason why I'm giving you this much time to turn it in is because I want a hard copy of the lab. And so the next time we meet is on this day. Now granted, this is an exam day. And so if you see it in the syllabus, it'll say, if the lab is due on an exam day, you can turn it in the following class period, which would be, or the following day, which would be the following Monday. I'll be on campus the following Monday, so you have to come to campus on that Monday to hand it in if you don't turn it in on the 29th. Okay? I'm not going to accept email submissions. All right? I want a hard copy of the lab. So make sure you turn it in on the 29th. Okay, and then the next one is on the 5th. So this one I will talk about next week. I know the schedule says I was going to talk about this one this week, but because of, well, a couple of reasons. I mean, really haven't gotten to DC circuits yet, and we haven't gotten to magnetism yet either. I pushed things back a little bit. Okay, so because of the schedule change earlier in the semester, I'm pushing these two back a little bit. So I can talk about this next week. You'll still have 2 weeks to do this lab anyway. Okay, this is probably the second longest lab of the semester in terms of the write-up. And so you better get started early on the DC circuit lab. Okay, there's a tremendous amount of error propagation in the lab. And then the last one's the next one's the DC motor lab. So I'll talk about these two next week. This is a project. You're going to build a motor and make it work. Okay. So you're going to be turning in a hard copy, a typed version of the lab, a printed out version of the lab on the 29th. That's the Ohm's Law lab. And I want to go over a couple of things that I require in the labs. In the lab reports, and they're mostly the same items as were required last semester if you took Physics 205 with Shakel. All lab reports have to be typed. Okay. Every part of the lab report has to be typed. All measured values must be reported to the correct number of sig figs. There's a typo there. All measured values must be reported with correct units. Now, if you have a table, make sure the units in the table are correct. And really, if you can put the units in the column heading for each column, you don't have to type a unit for each value in every cell of the table. As long as the unit is in the column heading, that's fine. All graphs are going to require proper captions, titles, axes, titles, and units along with the axes titles. All data points on graphs must be clearly visible. The only curve on the graph is the curve fit, meaning don't have the software connect the dots. So a lot of software, especially if you're using graphical analysis, you'll get a graph. and the software will just connect the dots. I don't want to see that, okay? The only time you actually have it connect the dots is when you have a high density of data points, so that to help the reader guide the eye. But you know, when you have your data points are spread out like this, having the software connect the dots is really bad practice. The only thing you should have is the curve fit. Or the line. So this is a no-no. I take off points for it, so I don't want to see that. You should just have one line or curve on it, and that's from the fit. When you use scientific notation, those three examples you see there are not, to me, are not valid. Your computer can do superscripts and subscripts, so I expect you to use proper formatting for scientific notation. Never, ever, ever, ever use the term human error for any reason in the lab report. That just tells me you don't know what you're talking about, essentially. Okay, it's a very generic term and students don't know what they're talking about. All graphs must show the curve fit parameters and their uncertainties on the graph. The raw values. If you have equations you got to type, use the equation editor. Don't handwrite them. And don't use the text format. Okay? Use the equation editor. If you're asked to show work in a calculation, show the equation and then show the equation with the proper values substituted into the equation. That way I know that you know how to use the equation. Okay. Go through the sample lab that was emailed to you. It's a resource. When you are given resources, such as simulations or a video on Canvas, use it. Okay, there's a reason for that. It's to help you to get through the assignment. Also, there's a set of announcements on Canvas in the lab shell. They contain the reminders that I'm going over right now. Labs that are copies from a previous semester or from sites such as Course Hero or whatever will receive a 0. And labs with fake or fudge data will receive a 0. These next couple of labs, you're supposed to learn how to wire things in addition to do the analysis. It's really important that you learn these wiring skills, especially if you're going to be an electrical engineer. Actually, if you're going to be an engineer in general. Okay? Questions? Okay, so I want to say a couple more things. I want to say a couple of things about the lab. Mainly the diode part, because in the diode part of the lab, it's a non-ohmic material. The circuit is a little complicated, but it's not too bad. Remember, a diode is a device that allows current to flow in one direction. And there's a lot of applications of diodes, and really I haven't had time to go into all different applications of it, but I'll send you guys a link with some information on the diode. When you do the experiment, if you measure the current through the diode and the voltage drop across the diode, you're gonna get a graph that looks like this. And in fact, the theoretical expression for the current I showed you this the other day, is given by this expression. And this is a curve fitting parameter. It's called a saturation current. You're going to use it as a curve fitting parameter in the lab. And n is also going to be a curve fitting parameter. So you're going to do a graph with really two curve fitting parameters. Theoretically, n is equal to 1. In reality, n is some number between 1 and 2, depending on the diode. And so you're going to do a curve fit of your data to this equation, and you're going to find I sub s and n. So you're going to get to see how a non-oblique material works. Now, this is not an equation that you use inside data, so you have to actually define this curve fit. Okay, and if you have trouble defining the curve fit, please contact me. All right. Now, this is the data here in table 3. And when you collect this data, you're either going to be on the 200 milliamp scale or the 20 milliamp scale. Which scale do you use? Well, you have to figure out what is going to be the maximum current. If the maximum current is less than 20 milliamps, use a 20 milliamp scale the whole time. If the maximum current is going to be above 20 milliamps and less than 200 milliamps, then use the 200 milliamp scale to collect all your data. Don't change scale as you're collecting the data, because if you do that, you're changing the resistance of your circuit, because the resistance of the ammeter changes between those two scales. Okay. Now you're also going to collect data for when you reverse the diode in your circuit. Okay, this is called a forward bias. There's the term. And then here's the graph down here is reverse bias. Okay, the current's going to be really low here. It tells you in the lab to use the microamp scale. Unfortunately, our multimeter does not have a microamp scale. The smallest scale is the 20 milliamp scale. So it's possible a lot of data points here will be 0. That's fine. If it's 0, it's 0. Okay, don't worry about it. It's because we don't have a great multimeter. If you were doing this on campus, we'd have better multimeters. But when you do the curve fit, only include the data from table 3. So this data is from table 4. So in the curve fit, only include the data. So only include this table. Okay? And I did go into video what V sub t means. And so if you don't remember, watch the video again. Any questions? I'm going to be on campus on Monday. After the lecture, I'll be on campus. I can answer your questions on the lab. So if you come to campus with your lab, I can help you with it. Okay, I can help you collect the data. Okay, especially for the last part. I'll probably be here next Friday too. I'll probably be on campus next Friday. I'm not on campus today just because I need to take off after 2 today. So otherwise I'd be on campus. All right, so I'll be on campus next week on Monday, and I'll be on campus next week on Friday. And my goal, hopefully, is that you're gonna ask questions regarding the lab. Questions, concerns? If you don't have questions, have a nice weekend. See you on Monday.
Already have an